So question 7, this seems to just start with the usual maths. Normal, isn't it? Mu doesn't equal 1,000, so it's a two-tailed test. 5% divided by 2.5% at each end. Under H0, X is a normal distribution with a mean of 1,000 and a standard deviation of 30, so 30 squared. But we're doing a sample of 10, and so the mean of the sample of 10 is normally distributed with 1,030 squared over 10. No central limit theorem needed because we're already normal there. Find out the probability that the mean is, they got 1,020, so we're going to go for greater than 1,020. There's no point in going less than, because that's clearly going to be too big there. And so just grab our calculator, stick that into our normal distribution mode, and see what it gives. So normal, I'm going greater than, X is 1020, standard deviation is the square root of 30 squared divided by 10. Yes, you can do 30 over root 10, of course you can. And the mean is 1,000, and that tells us it's going to be quite big, isn't it? So no, 0.0175, that is small. And so that is less than 0.0175 is less than 2.5%, and so we will reject H0. And we'll write the words as well. There is evidence that the mean weight of the flour in the bags is different to 1,000, or there is evidence of a change in weight and things like that. So part B, Olaf decides to alter the test so that the hypotheses are H0 mu is 1,000 and H1 is mu is greater than 1,000, but keeps it at 5%, so it's 5% one tail. Okay, so X bar is a normal, still got the same mean. This time it's 30 squared over n that we've got there. So the normalizing, to find the z value, we're going to do the value that we've got there, which is c, take away the mean divided by the standard deviation, which is the square root of this, so this is 30 over root n, and the probability that that being greater than this is 5%. So on the calculator here, I'm actually going to go with it doesn't matter about that one there, standard deviation 1, mean of 0, and we want this probability here to be 5%, and so the value I'm looking there is 1.6448 standard deviations above. So this is 1.6448. Actually looking at it, it's 4485, so 449. And I can rearrange that equation to find out what C is. Yeah, just timesing that up and adding the 1,000. So we got 1,000 plus 49.347 divided by root n. So that's what our critical value would be. And that bit there. So all of that is really a bit mathsy, really, isn't it? But the end bit here, this is what they've all been setting us up. So the type 2 error, a type 2 error, and the probability of a type 2 error is that. So that is the probability of accepting H0, giving that H0 is false. So we would accept H0, that is the probability that the mean is less than that critical value, given that X bar is a normal distribution. It's false, so they're telling us that it's 1020, and then here we've got 30 squared over n there. I think that's what we've got, and we know that that is equal to 0.005. Okay, take it slowly. Right, so normalizing this, we're going to go C, take away the mean, which we know is that, divided by the standard deviation, which is this 30 over root n, and that needs to be 0.005 in there. So I stick 0.0, so I'm just using my standard normal again, the 1 and the 0, and I'm putting a probability here of 0.005, and that's giving me minus 2.575 there, but it's actually 2.758. Stick that up there, and then put all of the, look, this is just a massive equation. So that thing there is going in there. This is just a big equation, all in terms of n, isn't it? And yeah, I have to confess, I've actually just stuck it into a n solve there and got 40 rather than tidying out all of that. So if n is 40, then C is 1007.8 as we work through all of that. Yeah, so started off with a nice first sort of normal maths question, but actually got quite complicated at the end there. But it is the end of the paper.